Thank you for inviting me. I'm not going to talk about semantic or goal-oriented communication, I'm sorry. But I will mention AI every now and then, so it's somehow related, at least to the way most people do semantic communications. Now, what I want to talk about is resilience and resilient radio access networks. Now, resilience has recently become a big topic, at least in Germany, for 6G. So when the ITU defined their key capabilities for 6G, they added this, oh, does this work? No, what's the pain? Ah, okay. So they have security and resilience here. And while they say it's an enhanced capability for IMT 2030, resilience actually was not part of IMT 2020, but just a side note. So security was there. Now, resilience, if you just take a definition, one is from ITU, is the capability to continue operating correctly and during and after a natural or man-made disturbance. It's about recovery. Now, what I was very interested in the last 2 years or so is to understand what resilience means, what's the end goal of building a resilient system. So what are we aiming for ultimately? And I'll try to shed some light on that. Now, recently in a discussion with Ericsson, Maciek Mühleisen said we could have made 2G resilient already. And I do not disagree with him, but it's a very good example of different definitions of resilience and different kinds of resilience. Now, when you think of 2G, we could have made it resilient by massive over-provisioning and with tight human control. And that would have had exorbitant cost. And what we would have achieved is maybe a resilient system, but that would be organizational resilience. Ultimately, it is enabled by humans, by human intelligence. That's the kind of resilience you aim for in manned space flight, for example. So you over-provision your systems, and then you hope to enable your humans on the space plane to repair and recover from disasters. While I'm convinced that when we talk about 6G and beyond and resilience, what we mean is operational resilience, meaning not relying primarily on human intelligence, but making the system itself capable of recovering from disturbances. That's operational resilience, and that's what I'm going to talk about today. Now, to give you an idea of what resilience is, take an arbitrary technical system. It runs at some nominal performance, let's call it 100% quality of infrastructure. And now in a robust system, when we encounter a disruptive event to our system, either the system doesn't care because it's not disrupted, or there will be some degradation in performance, maybe some adaptivity. In some cases, the system might even recover by automatic responses policies. But in general, when the event is disruptive enough, we will see degraded performance, and that degraded performance state will continue until some human comes to fix it. Now, that's a robust system. What can a resilient system do differently? Now, we have these widely published resilience strategies here. This is my variation of it. It's based on literature. So a resilient system actively anticipates and detects and absorbs disruptive events. So that's basically the same a robust system does, maybe with some more intelligence, but that's not what makes a system resilient. But after that, the system autonomously starts to heal itself. It works on its recovery. And that is, since a robust system has some adaptivity, which might lead to recovery once the disruption is gone, this is some more complicated process. And another part of the definition is that the system learns autonomously from the disruptive event and learns, self-evolves to hopefully recover faster in the future. Some colleagues also hope that the system actually becomes better over time to learn from its failures and improve its performance. I think that's science fiction, so I'm not going to care about this. I don't think it's part of resilience. We can be happy if the system actually learns to recover faster than before. Now, a question that came up in earlier versions of the talks was, that's a very nice understanding of resilience you do have there. Is that your definition? No, it's not. I did a long and exhaustive literature study to see how resilience is interpreted in engineering, and these are just logical conclusions from it. Now, a very good way, in my opinion, to explain resilience is a stepwise process. So you build a system. First thing you do is you make it work. We're happy that it works at all. And then you define some nominal operating environment. How does this work? No. There. So you define your nominal operating environment and you make it operate reliably in that environment. So you reduce the probability of failure. And once you're happy with that performance, you extend the range of possible operating conditions to off-nominal environments, to stochastic distributions. That's what we call robustness. So you build a car to operate in Europe, you make it work from -40 degrees to +50 degrees. Now you extend the operating conditions to -100 to +100 degrees. That's over provisioning. You get robustness. It's also some other mechanisms, but robustness is usually the step you take after resilience. And after reliability. Now, if robustness is working on large stochastical variations of your environment, then what is left for resilience is to remain operational under unanticipated conditions. That is, conditions you do not anticipate during the system design, and in terms of the environment that might mean a heavily changed environment that you cannot recognize anymore. Think there's a city, then there's no city. That would be a very strong example. Now, these unanticipated conditions, they are usually very high impact events with very low probability, and they are externally caused, so they do not originate within the system. Now, these low probability, high impact events, they are sometimes called black swans. It's 30 sigma events or 100-year floods or something like that. It's typically events you do not think about them being possible to happen until they happen. Yeah, like the black swan. We believe swans are only white until we discovered Australia and found black swans. And these probabilities are actually not really computable by scientific methods, because if you have only one data point, you can hardly make up statistics for this. Okay, another way to call these is unknown unknowns, while robustness is about known unknowns. So we know which effects can happen, but we don't know what values they will take, so we take a stochastic perspective. Now, one important thing is everything that improves reliability or what improves robustness also improves the resilience of your system. So everything we do and have been doing for the past decades was about resilience, but we just call it reliability or robustness if we do it. And nowadays we call it resilience, which I disagree with, because there's other names for it, right? So let's only call it resilience when we work on something that is not robustness anymore. Now, coming back to radio access networks, I see three main components to make your system resilient. I mean, one is situational awareness. You need to know what's going on, and you need, in some scenarios, you need a lot of data for that. You need a system architecture that gives you options. I mean, you can have the best control algorithms for resilience if you don't have any opportunity to reconfigure your system at all. And then there's autonomous control, and that's, at least when you think big, the whole RAN, the whole network, then autonomous control is at the heart of resilience. So, as I said, a resilient system is definitely more than a robust system. One core principle or core capability is autonomous adaptation to unanticipated conditions. and self-organized evolution, or at least to assist the human operator and be evolvable. Now, the big question is, how do we do this? Well, obviously AI, right? It's a solution to everything. There have been a lot of papers from our community that state that AI/ML is the solution. And if we just continue what we are doing, we will have resilient systems. I disagree, of course. Now, but this is only opinion, will be set by LLM specialists. So let's take inherently mathematical perspective towards this to see what statistical machine learning can do for resilience. Statistical machine learning, that's what we consider deep learning, LLMs, whatever you want to call it, okay? So we take a very abstract way to look at this. That's Richard Sutton's model of the intelligent decision maker. You have a decision-making agent that interacts with the rest of the world. The rest of the world can also be part of the system that gives you a reward for training, for example. The decision-making agent executes some action, and then it gets some observation and maybe a reward, and then it continues to do it. So the agent can be anything of appropriately high complexity. I don't care. It can be a scheduling algorithm, but more likely it's the control logic for a flying base station. As I said, it's just very complicated. We don't have an algorithm, and we desire to implement it as a statistical learning machine, what we call AI today. Okay, so this rest of the world, that's a probability space, easy to imagine. It's a huge thing. The nominal, or even the off-nominal operating environment, that's what I call N, is a subspace in this probability space. And a critical disruption, a big disruption that changes your environment, means a transition in this world probability space to another area of the probability space. So it's not a small disruption, it's a big disruption, okay? That's the mathematical model we have to consider to work with all possible examples. Now, what we do in statistical machine learning is we minimize a risk functional. So that's we have a cost function, which we call L. Then you take the average, the integral over the whole probability space, and you minimize it. That's what you do as empirical risk minimization in practical systems. That's your cost function. Now, this training loss function is fixed for training, and then you train. Now, this is, of course, a purely theoretical scenario because we know the world perfectly, the statistical description of the world. But in any practical training system, you have imperfect knowledge of this world. So this is just an outer bound for what you can do. So this is much better than you could do in a true system. Yes. Now, if we see a rare event happening, then by definition, the probability mass of this disruptive event space is very small because we start in the nominal environment. The event that brings us over there is very small. So the whole probability of that area is also small. We do know from math, that's very obvious, that integrating over a zero measure region, or so the probability is zero, then the integral is zero for that part. That's obvious. But the hope is that we can find a nice cost function that actually can handle these very rare but not completely improbable events. Unfortunately not. If we have anticipated conditions, which we know that while we do our system design, we can accommodate for the low probability in the cost function. That's what we do in ultra-reliable communications. But if we have unknown unknowns, unanticipated changes, we cannot account for that. And mathematics tells us, so I've done this convergence proof and looked at the limiting operation, but the point is when your probability goes very close to zero, you approach zero of the integration in a very good-natured way. That means you cannot have some magical loss function that accounts for all your rare events you don't know about. So it's a very simple result if you think about it, but this brings it beyond opinion and tells you you cannot handle all rare events, only those you can think about during system design. Obvious, but the hope was that LLMs can do it. Now, that tells us we have to do retraining, continuously observe the world, do continuous learning. So we can't do offline learning like you do in an LLM. You have to do some form of reinforcement learning, or however you want to call it. Now let's have a more practical view on the world. You have limited sensor resolution, and your work is only partially observable. So right now I can only see this lecture hall. I cannot look beyond that. I can't see Berlin. So the world itself is only partially observable. Now, how does this map to our world probability space? It means, I'm hitting always the wrong button. It means that the observed world of the system is some representation that maps very well to the nominal environment, but not much more. That's just good engineering. And the observation space has the cardinality that is much smaller than the real world. Now, if you have this very strong disruption where you have the state transition to a completely different part of your stochastical world, in your observation space, it means these nominal environment and the observed the disrupted environment, they overlap, they look the same in data. So the only way to map this is as a distributional shift. Now, we have the no-free lunch theorem. We cannot hope to train offline for this because we need to account for the distributional shift. Now, there's a distributional shift. You have to retrain your model in some way. That means we have to do domain adaptation, that's called online learning. There's two ways to do it. The first one is model-free agent. That's what most reinforcement learning algorithms do. So they don't have an explicit world model, they just build an implicit model. They gain experience, which you need for retraining, purely by experimentation with the real world. That's reactive control, that's adaptation, and it has very slow domain adaptation. The most widely known approaches, DPU networks and PPO, so policy proximity optimization, whatever, they struggle with these severe domain shifts. And you don't want your system to start experimenting with the real world in a disaster situation to learn how to behave in the changed environment. So the other way to do it is model-based agents. I mean, model-free learning is currently the most widely used, but model-based is another way. We build some internal model of the world in the agent. That's not necessarily a digital twin. It has to be a model that facilitates actually planning. And then you can use this model to simulate experience and adapt much faster to what's going on. Now, this model facilitates planning without experimenting on the real world. So one conclusion we can draw is if you do reinforcement learning or whatever, we really have to go for model-based approaches. And this model cannot be an arbitrary model. It should be causal because we're interested in domain adaptation, severe domain adaptation. So that means we have to do transfer learning. Transfer learning now requires an information transfer between different distributions, different models. And there's very strong theoretical indication, not by me, that the only information transfer happens over distributionally invariant features. And you can actually interpret these distributionally invariant features as causal effects. So causal effects goes beyond correlation effects. That's causal learning. It's a very difficult field, but it might hopefully help to adapt faster. Anyhow, so to give you an idea about the challenges involved in this reasoning, so that's for statistical machine learning, I don't think it's sufficient. But if you want to have such disaster scenarios, so your network is broken, you detect it, what a resilient system should do is deploy a UAV as an emergency network, and it should do this hopefully in the future without human control. Now, in that scenario, when you have a flood, that's probably a very good idea. But if your network is broken because there was a thunderstorm, you don't want to deploy your UAV before the thunderstorm is over. Now, think about all the decisions and the knowledge your AI needs to make a safe decision whether to deploy a flying base station or not autonomously. That's way beyond current LLMs. Because it needs real reasoning, which is a big challenge for nowadays AI. Okay, so I'm almost through. So resilience needs continual learning. It needs fast adaptation to change conditions. Statistical machine learning now today can't really do this. Model-based approaches might help, but not necessarily. And anyway, this is an AI topic, and it's at the forefront of AI research. We are communication engineers, and I'm not an AI researcher. So that makes me question, what am I supposed to do to make your mobile network resilient? I think that's computer science, but okay, I wanted to talk about this, but I'm not doing that. So the question is what we can do as engineers to contribute to that, while the AI people do their work and actually build agents that can reason properly. Well, we can prepare our network for this. For example, 3D network satellites, they do not give you resilience, but they give you a new structural layer you can reroute through. Now, that makes the network more robust, but if you properly get the stakeholders on the table and enable proper roaming procedures, the satellites can take over when your network fails. So there's, again, more than engineering to it. Another example would be if you have a disaggregated RAN, your RU gets disconnected, you want to continue operating over a satellite where you put the DU, then you have way more latency in your front haul than your network is designed for. So design your algorithms to be latency tolerant, way more latency tolerant, and to degrade gracefully. These are things we can do as engineers to make our network more robust, and making it more robust contributes to resilience. Build it flexible and reconfigurable to enable an AI agent to actually do something for resilience. That's all we can do as engineers, I think. Thank you for your attention.
Thank you very much for your nice talk. Are there any questions?
Yeah, I know it was boring. It's over there.
Like just about terms. So here you have anticipation there, right, in the
Yes.
circular. So we are anticipating unanticipated events here.
Yes and no. You anticipate that there might be a failure. So your system actually needs to be aware that there can be a fault happening. If your system doesn't monitor its condition, which is already quite a challenge in current systems, then you won't detect something is wrong and you can't react to it. So you anticipate failure.
Okay, failure. Yeah.
But that's the easy part, actually. Yeah.
Yeah, so I have a philosophical question after this, after your talk.
Yes.
So you talked about this probability space,
yes.
The omega. Is there anyone, maybe except of God, that can know this?
No, that's why we had this partial observability model later. Exactly. No one can know this, but even if you knew it, you couldn't design a loss function that accommodates for all the unanticipated rare events. So you can't find a magical loss function for your offline training. So your LLM can't work to handle all the unanticipated rare events, period.
Mm-hmm. So would it be that the upper part would be the practical part, and then you would have a like dashed line and everything below is
Look, we started with this very abstract model, which is an upper bound. And then when we talk about observing the world, then we have the observed world, and we have this argument that it is strictly a distribution shift. There's no other way to map this to your system model ultimately. So it has to be transfer learning you consider for this, which gives an argument that you need some form of causal understanding which goes beyond statistical understanding in your system. 30 minutes is way too less time to explain it properly. I'm sorry. Okay, thank you. One more. Okay, good.
So I wanted to know about, so you talked about the model free and the model based learning, right?
Right.
Yeah, if I understood it correctly, the model based learning, of course, you cannot model the unanticipated events in that. So you just model.
It's a model you build internally in your agent. So something like deep Q learning on all the other reinforcement learning approaches we use today, they do not build an explicit model that they can use internally to simulate experience. So it's hypothesized that it makes it more effective to adjust to changes in your world if you have a proper world model. You do have a world model in your brain. You know how the world will react to a lot of your actions. You can imagine that because you learned this as a child. That's something you do not have in current agents. Doesn't mean you can't build it in there, but that's what current AI researchers are actually working on, how to build these models in a way that works properly for planning, is not too complex, and is applicable. That's something Yann Lequin is currently working on, if you know his name. Thanks.
Thank you for the nice talk. So so your topic seems like something self-organized network or aligns with that. And I just wonder about the energy efficiency effect, because somehow I feel like if there's something, isn't it actually the more resource efficient that just put some labels there and then try to something, then instead of just observing with a bunch of sensors and then try to somehow run the AI models and then make it
You're absolutely right. But I mean, the question was, what does it mean to build a resilient system? So I take the definition, I think about what it means to make a radio access network, but a lot of other systems as well, resilient in the sense of these definitions. So the definition is easily written down, but if you think about the consequences of the definition, you end up with this. Resilience is never an optimal system because you always need redundancy, diversity, options to fall back to. So you will never have the most efficient system. There's a big question about cost. What can you do to make industry actually care about building a resilient system? I mean, that's very rare events. It happens maybe once in 10 years that you really rely on these methods you might implement. So there's no cost model behind it. That's a question for our society. How much resilience do we want? Do we want it? Do we have to force them? How do we force them? That's completely different questions. That's not engineering questions. I was just trying to figure out what the engineering question is, and it's very hard to find them, actually. Unfortunately. I wish I were able to write 3 proposals about it, but I wasn't. Because, yeah, it's very hard to do this, especially as a physical layer guy. I'm not in the business of self-organizing networks. It's an AI business anyway. Yes, thank you.
Great, thank you.
Eric.
So you had this result that the probability went to 0 with a linear convergence rate.
Yes.
Wouldn't that depend a lot upon these exact assumptions that you make on your
it depends.
functions here?
Yes. Yes and no. I mean, this is how the loss function behaves close to 0 measure regions. We know, the integral over an arbitrary loss function that is measurable. It's just a measurable function with respect to the probability space. That's the only assumption I make. And you fix it. That's your loss function. And then I look at the integral over this subspace D. Now we know that's very easy to show. That's common mathematical knowledge. If you take a zero measure region, the integration is zero. Enough said about that. But if you get very close to zero and you look at the convergence, some people might hope that your LLM can magically learn this. No, if you go close enough to zero, your integral will be very small, the integral of the sub area, which means it makes no contribution to your optimization problem for the minimization in your risk minimization. So it doesn't matter for training.
I see. Okay, sure. I mean, it just sounded like you would need some continuity assumption or something, but doesn't seem to be needed.
No, it just needs to be measurable because it's an integral. We consider the integration, not the loss function itself, the integration over the loss function. Okay.